This is your presenter Asloop Mudassar, and I am presenting slide number 94 of the course on laser physics. Question is, discuss unstable resonators with output mirror having variable reflectivity using geometric optics approach. The answer is, consider a two-mirror single-ended unstable resonator with rho of R as the field reflectivity profile of the output mirror, for example, mirror 2 of diameter equal to 2A2 and one round trip magnification equal to capital M. You see that this such a single-ended unstable resonator has been discussed in much greater detail in slide number 93. I would suggest to have a look first on slide number 93 and then visit this lecture. Let us designate the field incident on the mirror 2 by U2 of R. That is U2 as a function of R, where R is the radial coordinate at the plane of mirror 2. The field after one round trip is designated by U2 prime as a function of MR. The two fields are related through, that is U2 prime as a function of MR is equal to rho of R multiplied by U2 of R divided by capital M. Rho of R, as said earlier, is the field reflectivity profile of the mirror 2. U2 of R is the field incident on the mirror 2. Capital M is the magnification for one round trip of the resonator, and U2 prime of MR is the field after one round trip. The presence of MR means that after one round trip, the beam radius will be increased by capital M. The factor M in the denominator means that the field amplitude after one round trip will be decreased by capital M. Considering the fact that the field reflected by the mirror 2 towards mirror 1 will be the same after one round trip, apart from a decrease in its magnitude due to cavity losses, one can write that U2 prime as a function of R is equal to sigma times U2 of R. You see that on the right hand side, U2 of R is the field incident on the mirror 2, and on the left hand side we have U2 of prime. U2 prime as U2 prime is the field at the location of the mirror 2 after one round trip. And this equation has been written assuming that the magnification of the system is unity, that is capital M is equal to 1. But if capital M is not equal to 1, then we can write this equation in the following form as shown in equation number 2. That is U2 prime as a function of MR is equal to sigma times U2 of MR, where sigma is less than 1 is a real quantity accounting for cavity losses. Using equation number 1 and 2, we obtain, you see that the left hand side of equation number 2 and the left hand side of equation number 2 both are equal. So equating the left hand side of these both equations, we get the following equation as shown in equation number 3. That is sigma times U2 of MR is equal to rho of R multiplied by U2 of R divided by capital M. Here U2 can be identified as the eigen solution and sigma can be identified as the eigenvalue. The round trip fractional power loss due to diffraction denoted by gamma is then found as gamma is equal to 1 minus sigma square. We want to solve equation number 3 for two types of reflectivity, Gaussian and super Gaussian. We first assume that the field reflectivity of the output mirror as Gaussian. Then we can write this, that rho of R, or simply rho, you can write rho is equal to rho naught into e to the power minus R square over omega over Wm square. And you can also, if you want to write full detail, you can see that the left hand side is rho of R is equal to rho naught and then multiplied by the function which is of Gaussian shape, that is e to the power minus r square over wm square. If you set r is equal to 0, then the rho becomes equal to rho naught. That is, rho naught is the reflectivity at the center of the mirror 2, because at the center of the mirror 2 r is equal to 0. But when r is equal to wm, then the reflectivity rho becomes equal to rho is equal to rho naught over e. That is, rho wm is the distance from the center of the mirror by which the maximum reflectivity rho naught decreases by e. So wm is the distance from the center of the mirror m2 by which the reflectivity of the mirror would decrease by rho naught divided by e. Equation number 4 gives the amplitude reflectivity profile of a mirror number 2. The intensity reflectivity profile of a mirror 2 is found by squaring both sides of equation number 4. That is, so in the next to write the intensity reflectivity profile of a mirror 2, I need to take the square of both sides of equation number 4, which is shown in equation number 5. So capital R is equal to R naught multiplied by e to the power minus 2 times r square over wm square. This factor of 2 is due to the left hand side being squared and the right hand side also being squared. And this capital R is equal to the square of rho of R, and R naught is actually the square of rho naught. So where R naught is equal to rho naught square is the peak intensity reflectivity. So R naught, capital R naught, is the peak intensity reflectivity. Substituting rho of r from equation number 4 into equation number 3 and solving the lowest order solutions. So we are using rho from equation number 4. For example, over here, this is the rho of r. We are using rho of r from equation number 4 into equation number 3 over here. So substitute rho of r from the left hand side, which is rho of r, substitute to the right hand side over here in equation number 3 instead of rho of r at the place of rho of r. And then if you solve this equation for u2 of r for the lowest mode, then you will get u2 of 0. u2 0 of r is equal to u2 0 of 0 e to the power minus r square over w square, where this w is now equal to w square is equal to within the parenthesis we have m square minus 1, then multiplied by this parenthesis by wm square. The eigenvalue sigma is equal to rho naught over capital M. You see that this sigma is contained in the constant u2 0 of 0, but we have not given the full description of this constant. So this sigma is contained over here, and here I am going to give you the description that sigma is equal to rho naught over capital M, and this is the eigenvalue of the system. The output coupling loss gamma is equal to 1 minus rho naught square over capital M square. That is equal to 1 minus r naught over capital M square, where r naught is equal to, as given by r naught is equal to rho naught square. So gamma and sigma both are contained in this constant represented by u2 0 of 0. So but we are interested in the physics of that one rather than the full description of this constant. So we have sigma is equal to rho naught over m as the eigenvalue, and the coupling losses and the output coupling loss gamma is equal to 1 minus rho naught square over capital M square is equal to 1 minus r naught over capital M square. The corresponding radial intensity of the beam incident on mirror 2 is given by squaring both sides of equation number 6. So equation number 6 will give the amplitude solution. So the intensity solution is given by taking the square of both sides of equation number 6, which is shown in equation number 7. So I in is the intensity which is incident intensity as a function of r on the mirror 2. So In that is the incident intensity as a function of r is equal to I in 0 e to the power minus 2 times of r square over w square, where I in of R is the intensity profile incident on mirror 2. The field and the intensity incident on mirror 2 are both described by the Gaussian function. So you can see that the Gaussian function, that is e to the power minus r square over w square, is present in equation number 6, and similarly the Gaussian function e to the power minus 2 times of r square over w square is present in equation number 7. That is the amplitude and the intensity incident on the mirror 2 both have the Gaussian distribution. The intensity of the output beam, now the intensity which will pass through the mirror 2 and which will form the output part of the beam, that is the intensity of the output beam is calculated as given, that is I out, that is the output intensity as a function of r is equal to the input intensity incident on the mirror on the mirror multiplied by 1 minus r over r. You see that capital R is the reflectivity of the intensity, is the intensity reflectivity, and 1 minus r is actually the transmittivity through the mirror. So I in of r multiplied by 1 minus capital R of r will give you the intensity that will transmit through the mirror. And then its full description is given by using equation number 7, that is the full form of equation number 7 can be substituted over here, and then also full form of capital R of r. And you see that the capital R of r, the full form is this one. On the left hand side, we have capital R of small r is equal to r naught e to the power minus 2 times of r square over wm square. So using equation number 5 and equation number 7 into this form over here in equation number 8, we get the full form of equation number 8 as given on the right hand side, which is I in of 0. Within the square bracket, we have e to the power minus 2 r square over w square minus r naught into e to the power minus 2 times of m square r square over w square, which is not Gaussian. So you see that equation number 6 and equation number 7, that is the field incident on the mirror 2 and the intensity incident on the mirror 2, both have Gaussian profiles. But the intensity which is transmitted through the mirror 2 and forming an output beam is not Gaussian, as obvious from this term in the square bracket. Now I out of 0, that is I out at the value of r is equal to 0 is equal to I in at the value of r is equal to 0 multiplied by 1 minus r naught. That is I out of r. That is I out of r has a flat top at r is equal to 0. Because I out of 0, that is this expression, gives you the right hand side, that is this expression gives you a constant value independent of the value of r. That is the top, that is at the center of the mirror, you have a constant value incident on that one. So we can say that I out of r has a flat top at r is equal to 0 and can equivalently be obtained from. So if you take the double derivative of I out with respect to r, that is d square I out over dr square, and then you evaluate this double derivative at r is equal to 0 and set this double derivative is equal to 0, you will get the intensity. You can get a solution of I out at the value of r is equal to 0, that is in the center of the beam. So the information in the center of the beam can be obtained, that is the what intensity is incident on the mirror at the center and what intensity will leave out through the mirror to forming an output beam. The simplification leads to the condition. So if you set this condition and try to solve this condition, you will get that m square into r naught is equal to 1. Because in this condition, when you set this condition, you will get m square r naught minus 1 is equal to 0, which means that m square times r naught is equal to 1. And the out and the round trip cavity loss takes the form gamma is equal to 1 minus 1 over m to the power 4. You see that we have discussed gamma over here, that gamma is equal to 1 minus r naught over m square. So here you put the value of r naught from this expression, that r naught is equal to 1 over m square. So the gamma becomes equal to, gamma is equal to 1 minus 1 over m to the power 4. The geometric optics based results agree well with the wave optics based results for large values of equivalent equivalent Fresnel number, that is if the Fresnel number n equivalent is greater than 6, then the results obtained from the geometric optics as well will be the same as obtained from the wave optics. We are not going to discuss both. We have discussed only the geometric optics results, but we have not discussed the wave optics results. But we are just reproducing the result over here, that both results will give you that is the results from the geometric optics based results will be the same as obtained from wave optics when n equivalent is greater than 6 or greater than or equal to 6, because n equivalent is the equivalent Fresnel number. So you see that up till now we have discussed only the Gaussian profile reflectivity of the mirror M2. Now next we are going to discuss, next we consider super Gaussian reflectivity profile for the output mirror 2, which is defined as. So similarly, as in case of Gaussian function, we are going to define the super Gaussian reflectivity profile for the mirror 2 as rho of r is equal to rho naught e to the power minus r to the power n over wm to the power n. And this is shown in equation number 9. You see that for the Gaussian case, we put n is equal to 2. If you put n is equal to 2 over here, you will get the same profile as the Gaussian profile. But for n greater than 2, we get a profile which is referred to as the super Gaussian reflectivity profile. And similarly, if you want to obtain the intensity profile, you need to take the square of both sides of equation number 9, and you will get the intensity reflectivity profile, which is given in equation number 10. That is capital R as a function of R is equal to R naught multiplied by e to the power minus 2 times of R to the power n over Wm to the power n. And you know that super Gaussian distribution is actually the same as the Laplace distribution, for example. Laplace distribution is one of the examples of the super Gaussian profile. But the difference between the super Gaussian profile and the Gaussian profile is that the super Gaussian profile has more spiky peak and a longer tail as compared with the Gaussian profile. And you see that since we have the limit on the n, that is n should be greater than 2 for the profile to act as a super Gaussian, both for equation number 9 and equation number 10. So if you increase the value of n, for example, if you set n 3, 4, 5 and so on, you will notice that the curve will contract and the peak will enhance. So the contraction of the width of the curve of the super Gaussian profile will occur with increased value of n. So where n is greater than 2, the corresponding lowest order eigen solution is given by. You see that this is the solution. Such a solution has been given just for the case of Gaussian profile. But you know that here we are giving the same result without going into detail for the case of a super Gaussian profile. So the solution with the lowest mode for the super Gaussian profile is given, which is u2 of u2 0 as a function of r is equal to u2 at r is equal to 0 multiplied by e to the power minus r to the power n divided by wm to the power n, as given in equation number 11, where u20 is actually the Gaussian is actually the Gaussian solution, is actually the eigen solution. So u2 of 0 is actually the eigen solution, and u2 of 0 is actually the eigen value, you can say. Or more explicitly, or more implicitly, I would say that this u2 of 0 contains sigma and gamma as I have explained for the case of the Gaussian profile. But I am not giving you the full description of this one because that would require then more detail to be covered. So here W is equal to mn minus 1 whole raised to the power 1 over m multiplied by Wm. Here I need to make one correction in equation number 11 and for equation number 12, and the correction is that in the exponent you can see that Wm raised to the power n. This Wm should be replaced with W only. So the both exponent in equation number 11 and 12 should be read as e to the power minus r to the power n over w to the power n, not wm. So in both these equations, you can make the corrections where w is given by w is equal to mn minus 1 whole raised to the power 1 over n multiplied by wm. Wm is appearing in equation number 9 and equation number 10, but W will appear in equation number 11 and equation number 12, where W is related to Wm through this relationship, where M is the magnification of the system. And sigma and gamma remain unchanged. So sigma and gamma will be the same as in case of Gaussian profile. The intensity incident on mirror 2 is given by. So the intensity so the incident intensity as a function of r is equal to I in of 0 e to the power minus 2 r to the power n over w to the power n. So again here you need to write w to the power n and not wm. And you see that w is given by over here. That is w is equal to m to the power n minus 1 whole raised to power 1 over n and then multiplied by wm. So please make corrections in equation number 11, 12 and 11 and 12, that you need to replace wm in equation number 11 and 12 by only w. Okay, equation number 11 and 12 have super Gaussian profiles, but the output intensity has a non-super Gaussian profile as given in equation number 13. So you see that the output beam intensity will be equal to the input beam intensity multiplied by 1 minus capital R of R, because capital R is the intensity reflectivity and 1 minus R will be the intensity transmittivity. So this equation number 13 will give you the intensity of the output beam. And if you plug in these values over here, just like the way we have plug in for the case of a Gaussian profile as shown in equation number 8, and the right hand side of equation number 8 indicates that the profile is not Gaussian. Similarly, if you substitute those values over here in equation number 13, you will see that the right hand side will show you the expressions which will not be super Gaussian. It has been found that the mode area AM is the area of the nth mode increases as n is increased, providing better opportunity of exploiting the cross-sectional area of the active medium inside the resonator. But the diffraction angle or the angle of divergence of the output beam increases with the increase in n. So you see that I am not giving any mathematics in support of this paragraph, but just remember that the mode area, that is the area corresponding to the nth mode, and you know that mode is actually the longitudinal mode over here, which means that a mode which is wavelength dependent. So here we are talking about the nth mode, and AM is the area of the nth mode. So this area will increase, that is the concentration of the nth mode will increase when we increase the value of n. And this provides us an opportunity to exploit the cross-sectional area of the active medium. Because with the increase of n, as said earlier, the super Gaussian curve will contract and will be more concentrated. So more concentrated light will be incident on the active medium cross-sectional area. So which means that we can also enhance due to that one, the mth area of the mode will also be enhanced. But you see that when we contract the beam, what will happen? The diffraction angle or the beam or the divergence of the beam will increase in the output beam with increase of the value of n. So more you contract the beam within the resonator, within the active medium, then the beam which will leak out, which will be an output beam from the mirror too, will have more divergence due to the diffraction involved. So it has also been observed that as n increases, the optical power from the center of the beam starts drifting towards the beam edges. It has also been observed that as n increases, the optical power from the center of the beam. So look at this, is very important, that the that the optical power from the center of the beam starts drifting towards the beam edges. This is again a statement which I am not quoting over here, but just giving you a statement. The beam brightness, which is proportional to AM over theta d square, where theta d is the angle of divergence of the beam. So AM over theta d, to which the beam brightness is proportional, has an optimum value and is a function of n. The value is determined by R naught and capital M. So the brightness, the value of the brightness will be determined by the value of R naught and by the value of the magnification of the system parameter capital M. Super Gaussian profile with n from 5 to 9 is a good choice for variable reflectivity unstable resonators. So you can choose n value from 5 to 9 if you want to make your resonator to have a variable reflectivity. For example, variable reflectivity for the mirror number 2, through which we are obtaining the output beam. Because we are discussing a single-ended unstable resonator, it means that the output will only be obtained from one of the mirrors, and here we are obtaining the output from the mirror 2. So I think that this is appropriate to give answer to the query raised in the question. So this is the end of slide number 94.